Here is a diagram that will help you further visualize and understand what is going on here. Okay, so I have f(x) and y. Let's say x is age. Right? This is a good example. And then y, let's say that is height. Okay, so again, the idea of regression analysis is trying to explain height, right? Explain the deviation in height. Right? Why doesn't everybody have the same height? Right? That's kind of a trivial or kind of seems like a simple, ridiculous question, but that really is what regression analysis is trying to do. It's trying to explain why doesn't everybody have the same height. And so here we can say, well, people have different age, right? And so you can let's say that that's 20. Let's say that those are 20-year-olds. But then what this point then represents the average height of a 20-year-old. Right? Now, obviously, among 20-year-olds, they are different heights. Right? So some 20-year-olds are shorter, some 20-year-olds are taller, but most are going to be around the average. Right? And now we can take the slice. So imagine if we just take all the 20-year-olds and then we cut a slice out. So we can cut a slice out. Right? So this will be so this will be all the 20-year-olds, right? And this mu here will be the average height of 20-year-olds, and here will be the y, the height. But this is a conditional now because I'm not looking at any other age. So this is really a conditional on y given the x equals 20. As this is so I'm looking at all the 20-year-olds, right? And then now here I can get this two-dimensional curve. Okay? We'll talk a little bit about, here, let me slide down. We'll talk a little bit more about why this will be a normal distribution, right? A little bit later. Okay, so go ahead and open up Gradle. We'll need this for the next section here. And let's go ahead and use let's do a new data set. And let's go ahead and use the same data set as our previous example in 14.2. So that was our production. If you remember, that was our production example. Go ahead and just put in the number observation 6, cross-sectional, moving forward, right? And we can start entering data value. Okay. And just in case if you forget, right? This is the data set that I'm talking about. Right? It is this production volume, production and costs. Okay, so now let's the first one we want is units, and also make a note. The last video there was a when I input the data, there was a mistake in one of the data values. Okay, so now when we run the regression again, the number is going to be slightly different. So just be aware of that. Enter, check, add another variable. Okay. Let's call it TC. Right? Let's use the same variable names. There. Okay. Check. All right. Close that. So now we have the two variables we want. Okay. And then I want to run, again, ordinary least square. Okay, the dependent variable, right, the variable that we're trying to explain is total cost. And then we're trying to use volume, right, to explain total cost. Okay, run that. All right, so now that we have our estimated parameters here. Those are our coefficients. Let's go ahead and write those down. So this is our beta naught, and beta 1. Okay, so coming back to our page, here is our regression. Here's our regression estimated regression equation. Right? And so, what do I want this? Okay, so let's say, for example, right, when x equals 500, right, then what will the total cost, how will total cost be distributed? Okay? So to answer the question, we'll say, well, total cost hat, sorry, let's just say TC here, right? TC equals 1246.67, 500. Okay, let me just calculate that. Okay, so that would be 5046.67. All right, now my point is, how do we interpret this? So the way we interpret this number is, this is the average total cost to produce 500 units. Okay, all right. So, also this will be our best estimate. So the idea is, right, if you needed to predict how much would it cost to produce 500 units, right, that your best guess will be the average. And why is it the best guess? Well, because among all of the ways that we can produce 500 units, right, the total cost is going to be distributed like so. Right? Here's our total cost hat. Again, there's this condition on that we are producing 500 units. It is centered at 5046.67. So sometimes sometimes it will be cheaper, and sometimes it will be more expensive. Okay, but most of the time it will be centered around here, and so that will be our best prediction. Now, why is it that this is normally distributed? Why am I drawing this? Well, actually, we made some assumptions, or we just didn't talk about it yet. But we actually made some pretty strong assumptions in order for us to proceed and draw this normal distribution. Okay, so the variation, these variations all come from, right, epsilon. More specifically, it comes from the standard deviation, right, of epsilon. Okay, and so what so it's not really from now on, is that we've been making this assumption, right? But whenever you do simple regression analysis, this is the basic assumptions we make. So the assumption is, right, that epsilon I, right, will have a normal distribution. Okay. Furthermore, the expected value of epsilon I equals 0. Okay. What this means is, right, that so if you look at this, that means they will be equal. It is equally likely that the total cost will be below 5046, and total cost will be above 5046. So there's no skewness in the variation. Okay? If you look at this picture here, right, same idea, right? If we look at 20-year-olds, that means that they are same. They are in the population. They are same number of people, same number of 20-year-olds that's below average, and same number that's above average. Again, no skewness. Okay, so that's what this. Represents. Okay, and then we also make the assumption that variation of epsilon is greater than 0. Okay, this simply just means that there is variation. Right? The variation does exist. Okay, and finally, we'll make another assumption that all epsilon I are independent of each other. Oh, excuse me. They are independent of each other. Okay, all right. Now, if you continue on to study statistics, right, one of the first things you would do in a higher level stats class is to start relaxing these assumptions, or you will learn, what happens when these assumptions doesn't hold, what happens to your result. Okay, but for us to as an introduction to regression, right, we're going to assume that all these assumptions hold. Okay, all right. Now, sigma here really is no different than the sigma that we're used to. Right? It is the standard deviation. Okay, just the standard deviation of epsilon. Now we would like to estimate it because it is a population parameter. Okay, now so the estimator that we will use is called mean square error, MSE. Okay, by definition, right, that is like so. So S square equals MSE, which equals SSE over n minus 2, right? Remember, this is the degree of freedom of the model. Okay? And now remember what SSE is. SSE is the summation of EI squared, okay, n minus 2. Right? And this should make intuitive sense. Right? The variation, the variation, again, here's the variation that we're talking about, right? How far is the population away from this regression equation, right? So, if we observe, here's our predicted line, y hat I, right? If let's say the data, right, the line, right, accurately, like, predicts the data, then EI will be small, right? Therefore, it should indicate that sigma, right, in the actual population is also small. Vice versa, right? If the line, right, doesn't predict the variation well, or the variation, right, has widely varies widely from the line, and then this will indicate, right, this will indicate, right, a very large sigma, right? So that's why we use this to estimate sigma.